Hello and welcome back. We are going to be doing section 2.3 today. We're going to be doing some rules that we can use when we're talking about limits. And we're going to go ahead and start where C is a constant, meaning it's a real number. The limit of as x approaches a of f of x and limit as x approaches a of g of x both exist. So we're assuming that, that we don't get an infinity situation or something like that going on. Then we can actually conclude a couple of things. That the limit as x approaches a of f of x plus g of x, and that's plus or minus, is the same as the limit as x approaches a of f of x plus or minus the limit, meaning we can break it up. So we can break them up into two separate limits. The nice thing is we can bring these limits into any part of the function of x as necessary to see what the behavior is. So the limit as x approaches a of a constant times f of x, meaning I can bring that constant, meaning that it's a constant relative to the variable x. We can just bring it on out. Even if it's a function of another variable, we can still bring it out. Our third rule is multiplying. And like the addition and subtraction, we can break it up. And the same thing goes for division. We just break it on up. And these may seem superfluous to you, but come in very, very handy later in the semester. Maybe even today. And there are a couple of exponential ones. This can become, again, just bring that limit on in. Inside, and in fact, we can even for our sixth one, the limit as x approaches a of b to the some function of x, we can make this b raised to the limit. And that's all in the exponent there. So all of these rules can hold true and will be used. And let's practice this a little bit with our example. I have a weird typo. All of that should be here. So we'll just sort of ignore that and rewrite it here. So the limit as x approaches 2 of f of x equals 4, of g of x is 5, and of h of x is 8. And using our rules, we can actually break this up and just replace the f of x with a 4, the g of x with the 5, the h of x with the 8. And very nicely, that gives us a negative 1/8. So we do have a limit for that. Number 2, we can also just break it up using our rules here. So this is going to become 6 times f of x as x approaches 2, we get 4, times g of x as x approaches 2, we get 5, plus h of x, which is 8. And that's looking to me, 6 times 4 times 5 plus 8 is going to give us 128. And for number 3, this becomes the limit as x approaches 2 of g of x, using our fifth rule up here, to the third power. And that limit is right here. That's 5 to the third power, which is 125. So on to bigger and better. All right, so we're still going to need these rules, but we're going to scooch the paper up a little bit. And how do we actually find a limit? Well, ideally what I want to do is I want to take that x value and pop it into here. And so that's always going to be our default. We're always going to start there. The only time we won't do that is if we end up dividing by 0, or we end up taking the square root of a negative, or something crazy is happening. Usually it's dividing by 0. That's the issue. So this becomes 2 times 3 squared. So again, when you're trying to take a limit, try just dumping the number in and see if you get something. So what is this limit? It is 13. So we're going to do the same thing here. Let's just try dumping 2 into there and see what we get. And let's see what we end up with. This ends up being 8 times 2 is 16. 16 plus 9 is 25. That is 6 minus 1, which is 5. That is 8 plus 1 is 9. This limit is just 10 over 9. So you can see so far it's just order of operations. Of course, it's obviously going to get more complicated than this, where we're not going to be able to always do this. For example, part 3. Now you'll notice when I put a 2 into here, 2 squared is 4, 4 minus 4 is 0. So we have an issue. We can't just dump this in. But what we can do is factor the numerator and denominator. And this one obviously has been fairly well designed, where we can just reduce it out like that. And we end up with, and by the way, you might be wondering, do I have to write the limit as x approaches 2 every single time? The answer is yes. And math teachers are usually really weird about that. So you're going to have to really specifically do that every single time. Meaning you'll probably get docked a point or 2 for not doing that. And you might be saying, hey, you just skipped writing limit. Well, I'm actually taking the limit. Once you put the number in, there's no more limit involved. You can see that here, there's no more limit. You can see that here, there's no more limit. So you have to write limit each time until you actually take the limit. All right. Now for number 4, we're going to get a little fancy here. And I want us to recall a rule we already know called the difference of squares. We, of course, just use that here, right, in the denominator. But instead of viewing it as it's this number squared and it's that number squared, we're going to go the other way. I'm going to say it's this square root that gets me there, and it's this square root that gets me to the b. So this limit here is going to be the square root of that minus 1, and the square root of that plus 1. Now, if you FOIL that back together, you'll see that the inner and the outer all kind of collapse out, and we end up back here. So you can see this reduces. 1 of 1 over the square root of x plus 1. And now I can actually replace the 1. And by the way, I didn't mention, if you replace the x with a 1 right here, you get 1 minus 1, 0 in the denominator. Again, that's problematic. So this gives us 1 over square root of 1 plus 1, which is 1/2. Now, for number 5 down here, we're again going to have to get a little fancy. I'm going to go ahead and FOIL this out. And just real quick as a review, not that we need it. When I square a binomial, like I'm doing down here, I use this pattern here, where a in this case is the 3, b in this case is the h. And we get this. And again, you can see if I plug in h equals 0, now I'm again dividing by 0, which is obviously a problem. But you'll notice here, when I FOIL it out like this, the 9s in this case are gone. Which is good for us, because now in the numerator, everything has an h, which means I can factor an h out. Which very nicely reduces. Now when I plug in a 0, this limit is just 6. All right. Now you might think that seems fairly convenient that happens, but this process, again, this is actually that difference quotient that we talked about in the previous video, where that will always happen, where we'll be able to reduce out an h like that if we know our algebra well, which is always tricky. All right, let's come up with a few more fancy tricks for finding a limit. So in this case, number 6 here, what we're going to do is we are going to rationalize the numerator. Now, if you don't recall, we have to use the conjugate. And I want to point out, we're going to be forcing this rule here. These two are called conjugates. And we are going to force that condition for the numerator of this problem. Now I have something minus 3, which means I'm going to have the same something plus 3. In this case, t squared plus 9. By the way, as I mentioned, if you take the t equals 0 and you plug it into there, again, I'm dividing by 0, so that's a problem. So we're going to have to do one of these tricks, but your goal should always be trying to plug that in. And we end up with again, I'm forcing this condition here. So it's going to be that first part, A. A in this case is the root t squared plus 9. B in this case is the 3. So I'm going to end up with t squared plus 9. So the square root squared is just that, minus the 3 squared is 9. Now down below, we have t squared times square root t squared plus 9 plus 3. And you can see the 9s cancel out, which means I have t squared by itself, so those reduce out. So those are gone, and then that reduces there. I'm left with 1 over. When I plug in 0 there, I get 1 over. So 0 there is going to give me a square root of 9, which is 3 plus 3, or 1/6. Now, for part 7 here, we have a problem. What we're going to have to do in this case, and you can see we're approaching 1 from the left side. Now notice when I just plug, I'm sorry, -1. When I plug in -1 here, -1 plus 1 is 0, so that's out. We can't do that. And what I'm going to do is I'm going to go to my calculator, and I'm going to plug in x plus 3 over x plus 1, and I'm going to plug in some numbers close to that to see if there is a value. Let's try not to get a glare there. All right. So this is going to be x minus 3. Now remember, x is here. X minus 3 divided by x plus 1. X plus 1. And I'm going to test some values like I did from a previous video. Vars, y vars, function y1. And I'm going to test that at a number close to -1, but to the right of -1. And so I'm going to test, parentheses, -0.9999. Ooh, that looks like it's going up to -infinity to me. So this is going to go to -infinity, which means the limit does not exist. Let's do it again, but let's go from the other side. So it's same function, same function. So vars y1. And now I'm going to go -1.00001. I'm going to guess that's positive infinity. And we're getting a huge number. So this is going off to positive infinity. Which again means that it does not exist. The limit itself does not exist. And number 9, we can actually factor some stuff out in that case. It's just x to the first power, pardon me. And that's going to be x squared minus 5x plus 6. And although the negatives reduce, and one of the x's reduces, nothing else reduces, which means I'm going to have to resort back to my old-fashioned way of doing stuff. That's filling this with the function. So negative x to the third. Nope, I need parentheses. Parentheses, negative x to the third. Plus 5x squared minus 6x. Close, divided by, parenthesis, negative x to the third minus 4x squared. And we're going to evaluate that to a number very close to -4. So we'll let x be, so let's do vars, y vars, function y1 of -3.99999. See what we get. Ooh, that's a big negative x, negative infinity. Which again means that it does not exist. All right, just a few more. Now here's the good news with this one. In fact, let's draw this out. So first off, we have a line that is here. And when x equals 1, you can see we're going to be up at 2. So we are going to have an open circle right here. Otherwise, we're going to have a straight line with a slope of 1. And when x equals 1, we are going to exactly be, so that's 3 there, which means we're going to be up here at pi. And we want to know the limit as x approaches 1. Now, here's the thing. The limit has to be the same from the left direction and the y direction for the limit to exist. So as we are approaching 1 from both sides, y is approaching 2 from both sides. So this limit is 2, even though g of 1 is equal to pi. Right, at 1. So the limit and evaluated the function at that value are two different things in this case. All right, for number 4, I want to take us back to an old definition. Something you learned in an algebra class whenever ago. That the definition of the absolute value of x is x if x is bigger than or equal to 0, meaning if it's positive, and it's negative x if x is negative. Which means, as we are looking here, we're going to have to break this up into 2 separate limits. So if I approach this from when x values are negative, this means I'm going to get negative x over x by definition, which is negative 1. And the limit as x approaches 0 from the positive direction is going to give me a positive x over x, which is a positive 1. And here is the problem. The limit from the 2 different directions are different. Therefore, the limit as x approaches 0 of absolute value of x over x does not exist. It can't exist because we're arriving at 2 different values. All right, last part of this video is something called the squeeze theorem, sometimes called the sandwich theorem, depending on which textbook you're looking at. They are the same theorem. And the theorem states that if f of x is less than or equal to g of x, which is less than or equal to h of x, meaning we have a y values of a function that are always between the y values of 2 different functions, and the limit as x approaches a value of f of x, the smaller, is equal to the limit of the larger, then our conclusion, and the limits exist, then the limit of the one in the middle has to also equal that same limit. So picture this. You have some function that's always above, and it's approaching, we'll say 0 in this case. We'll call this the f of x. You have another function that's always smaller, but is approaching the same limit. And then you have another function that's always in between. Then that red function must have the same limit as the other 2. All right, that brings us to our last example. We're actually not going to do number 6 here. So we're looking here. And what's going to happen is I'm going to take the function. Now we know sine x, and as x approaches 0, that means that x value is very small. And we know sine is always between -1 and 1. So I'm going to have two functions, -1 and 1. We can have the equal to symbols there. That's fine. And now to make it match this, I'm going to multiply through by x squared. And now you can see I have my function. And we know that the limit of the smaller function is here. And the limit of the upper function, right over here, is also here. And this function is between. Therefore, we have to conclude that the limit as x approaches 0 of x squared sine of 1 over x has to also equal 0. This is by the squeeze theorem. And there you have it. I hope that was helpful.